Bismillah ar-Rahman ar-Rahim. Assalamu alaikum everyone. I hope all of you are doing well. Remember we have talked about variables and we talked about how to measure variables. Today we're going to talk about two very important topics, reliability and validity of these measures, because measures can have errors, and we'll talk about the source of errors of measures today and how to avoid them. Before we get to that, I would like to go over this table, which might summarize some of what we talked about last time. This is from the SINS study that we talked about last time. So it had several dependent variables: muscle strength, muscle endurance, functional limitation 1, 2, and 3, and then disability. How did they measure this variable that's called muscle strength? They measured it, so the measure is maximum or maximal weight lifted one time in kilograms. So this is the measure of this variable. How do you classify this measure or the type of this measure? It is ratio, because remember, ratio means a continuous variable that can carry any number, that can have fractions. If we look at the variable that is called muscle endurance, for muscle endurance, they measured, the measure is number of repetitions lifting 90% maximal weight. And again, it is a ratio. Functional limitation 1 was measured by time required to rise from a chair in seconds. So how much or how many seconds the person would take to get up from a chair. Again, this is a ratio measure. A stair climbing power in watts. Distance walked in 6 minutes. This is the 6-minute walk test. Again, it's a ratio. Another variable is disability, and they did the disability on a self-report, which means the person fills out a form on a 0 to 3 scale, without difficulty, with some difficulty, with much difficulty, or unable to do. So the self-report is from 0 to 3, so it's 4 options. And it is, of course, an ordinal scale, because it can't carry any number. It has to be either 0, 1, 2, or 3. And it cannot have fractions, and it is ordered. So that's why it is an ordinal scale. So I thought this is a good table to summarize some of the concepts that we talked about last time. Now, the measures that we're talking about, like the measures that we just talked about, how accurate are our measurements? How accurate are these measures? If these measures are perfect, then everything we measure is really a true value. So if measures were perfect, then every score would be a true score, or a precise reflection of the variable of interest or the phenomenon of interest. However, as you all know, nothing is perfect. So with every measure, there is a margin of error. So we don't know the true value. This is, we measure something and this measure has some type of error. So the measures that we get are combination of the true value, whether it is blood pressure, range of motion, muscle strength, any measure you can think of, it is true. In this case, could be a signal like EMG, and some error. So every measure is a combination of a true value and some error. In other words, if we think that X is the measurement, T is the true value, E is the error, then whatever we are measuring, which is the x, equals the true value plus or minus an error. So the error is not always with a plus. The error could be with a minus. If I have a blood pressure machine that is always recording or reporting a blood pressure that is 10 millimeters of mercury below the true value, there is no way of knowing the precise value of T and E. When we measure, we don't know what is the true value and how much is the error. That's why we need to estimate this error by calculating the reliability of the measure. What is reliability? So the error could be either systematic or random error. The systematic error is from the name systematic. It happens every time. A random error doesn't happen the same way every time. Let's assume we are measuring range of motion of the knee, for example. You all know to measure the range of motion of the knee, you need to put the center of the goniometer on the lateral epicondyle of the femur. So that is a landmark for the goniometer. You need to align it with the landmark. If you consistently miss the landmark and put the goniometer 2 centimeters in the front or 1 centimeter in the front, so this is a systematic error, meaning that you are making the same mistake with the exact same measure every time. If I'm doing manual muscle test and I'm always applying the force at the wrong location, so for example for knee extension, and instead of putting my hand right above the ankle, I'm putting my hand in the mid leg every time, then I'm consistently applying the force at the wrong location. If I'm testing joint play and I'm not putting the joint in the loose pack position, which is the joint plane, that will result in a consistent reduction in movement. The joint is not going to move as much as if I put it in the joint plane. And if I'm doing this consistently, then I am creating a systematic or consistent error. Random errors, on the other hand, happen when we do things in random. For example, let's stick to the goniometric measurement of the knee. If I'm always missing the landmark, but one time I'm missing it by 1 centimeter, one time I'm missing it with a half a centimeter, one time is behind the lateral epicondyle, another time it is in front of the lateral epicondyle, then I am creating a random error every time I'm measuring knee range of motion. For manual muscle test, again, if the amount of force that I'm applying, like one time I'm applying a lot of force to define what the normal or 5 on the scale, and then the other time I'm applying less force, then this is random variation because I don't know how much I'm applying every time. I'm not duplicating what I did last time. For the joint play, again, the force applied, if I'm pushing on the joint, one time I'm pushing really hard and the other time I'm pushing really light, then I am creating a random error. So errors can be systematic or can be random, and both of them are errors in the measure. The error could be, the source of the error could be the person himself, the person who is doing the test. So it is the tester or the rater. So the person himself is not doing the test correctly. Sometimes it's not the person, it is the instrument that the person is using. Whether the instrument is a goniometer with a loose center, maybe, whether it is a whatever you might be using, a isokinetic machine, a reflex hammer, even the disability questionnaire or some self-report instrument could have some errors as well. So the instrument itself could create an error. Again, the instrument itself could create a random error or a systematic error. Sometimes the tester is perfect, the instrument is perfect, so no errors, but the variable itself is changing. So variability of the variable, variability of the characteristic being measured or the variable being measured sometimes is creating an error. For example, straight leg raise or height with time of day. So when you wake up in the morning, you try to touch your toes, you're not able to touch your toes, you're still a little stiff. As the day goes on, you have more straight leg raise. As that you get warmer and you move more, the straight leg raise, your straight leg raise is increased. So in this case, if the tester is perfect and the goniometer is perfect, but the variable itself has changed, then that will create an error. For example, if I'm asking a person with plantar fasciitis, how much pain do you have? If I'm asking him that question early in the morning, he'll probably have a lot of pain. As the day goes by and the person is walking on his feet, the pain will start to decrease. So depending on when during the day I'm asking the question, the answer might be different. So now we have a different answer because of the time of day that we asked the question. Ligamentous laxity in females varies with the time of the month. So in sometime during the month, for young women, they could have more ligamentous laxity than other times of the month. Although this specific variable is kind of debatable, we can discuss this, but let's assume that it changes. The strength may vary with the person is fatigued. So if the person is tired, you can, for example, when you test the muscle strength, you can give them a low score because they are just tired, not because they are weak. So in this case, all of these variables are creating variability and creating different answers because they change according to the circumstances. So the sources of error could be the tester, the instrument, or the variable itself. That's why we need to make sure that what we measure is reliable. That's why we need to look for ways to establish the reliability of our measure, to be able to be confident in what we measure. So what is reliability? Reliability is the extent to which a measurement is consistent and free from error. So the measurement has to be consistent and free from error. The word reliability can be referred to as stability, consistency, reproducibility. All of these words have the same meaning, which in simple English means if I'm measuring something and I measure it again, it gives me the same reading or very close to the original or the first reading. I can't measure somebody's blood pressure at some point and then after 5 minutes I measure it again and find 20-point difference in their blood pressure. That would be crazy. The measurement has to be reliable, so with repeated measures I should get very close numbers. Okay? Determination of retest reliability. How would I determine retest reliability? To test someone at point 1 and retest the person at point 2, how can I make this measurement or how can I tell if this measurement is reliable? There is something called reliability coefficient which can be calculated statistically. If the variable is an ordinal variable, interval variable, or ratio variable, the best statistic that can measure reliability is called interclass correlation coefficient, or ICC. The ICCs, or the interclass coefficient correlation coefficients, range from 1 to 0. 1 is the best correlation coefficient. It means that this measure is perfect on repeated tests. If it is 0.6, 0.5, 0.4, then it is moderately reliable. If it is below that, then it is really not reliable. What if my measure is a nominal measure or nominal data? To determine reliability for nominal data, there is something called kappa statistics, and we can calculate this with software. And you will see this, I'm sure, in the articles that you have reviewed. You have seen, and many of you reported that the authors are saying that this instrument has been tested for reliability. And the reliability coefficients, or the interclass correlation coefficient, is 0.9 or 0.8 and so on. So if the measure is ordinal, interval, or ratio, then we use interclass correlation coefficient. If the measure is nominal, and you know what that means, then we use kappa statistics. To measure the instrument reliability or reproducibility or retest reliability, the instrument is used on 2 separate occasions with the same subject. So I have the same person and I use the instrument at point in time, point 1 in time, and then I use it again at point 2 or time 2, and then see how much difference between time 1 and time 2. How much time should I allow between measurements, between time 1 and time 2? This is a difficult question. And it is difficult because if the time is too short between the two, and I'm measuring, for example, if my measure is muscle strength, then the person might be fatigued. He might be not motivated to continue. He might have learned what to do, and this learning effect can improve his performance. So all of these factors can affect the measure if the time allowed between time 1 and time 2 of measurement is too short. If it is too long, then the variable itself maybe changed. For example, maybe the person got stronger, maybe the person got weaker, maybe the person got more flexible, and so on. So every researcher determines the time of measurement according to his or her knowledge of the variables. So if it is too short, again, it's not a good thing. If it's too long, it's not a good thing. But what is too short and what's too long depends on what you are measuring. So instrument reliability means that the instrument is able to measure a variable consistently over repeated measurements on the same people or the same person. Then rate of reliability: can a person measure something twice and get the same measurement? This is called intra-rater reliability. Intra means you're comparing the person to himself again at time 1 and time 2. If the person is consistent, that means the measurement, the intra-rater reliability is good for that measure. If every time the person is giving a different measure or different value, then it is poor reliability. Things that can happen with intra-tester reliability: the person can improve with multiple measures because of training. The rater himself could be biased. If the rater measures something, he knows the answer, he knows how much he got the first time, and then he measures the same person again, that might bias his measurement. It means that he remembers that this range was, for example, 70 degrees. Then when he measures it again, he tends to get the around 70 degrees again because he knows that this was the original measures. That's why it is very important in some studies to blind the rater on the measurement, meaning they remove the numbers from they put a sticker on the numbers of the goniometer and have the person measure, and then another person looks at the number, so the rater himself doesn't know what number was registered when he measured. So one more time, intra-rater reliability is talking about the same person measuring the same measure several times and trying to see how much difference between multiple measures. Inter-rater reliability, however, talks about the agreement between raters. So rater number 1 and rater number 2, or therapist 1 and therapist 2. If therapist 1 is measuring the knee range of motion or the hip range of motion and gets a number, and therapist number 2 measures the same thing and gets a number, are they agreeing on these numbers? Did they get the same measurement? Did they report at the same angle? If they did, then there is a high inter-rater reliability for this measure. If they didn't, then it is poor inter-rater reliability. Again, interclass correlation coefficients is the best test for continuous data, which is most of the data that we use as physical therapists. Again, it is good for intra-rater and inter-rater reliability. Keep in mind that ICCs, again, between 1 and 0. 1 is the best. Nothing is 1 usually. It is, if it is in the 90s, that's wonderful. But if it is in the 0.5 and so on, it is not a reliable measure. One concept that's very important to remember is the difference between correlation and agreement. You probably all know what correlation is. Correlation is when two variables behave in a predictable way. Positive correlation means if one increases, the other one increases. Negative correlation means if one increases, the other one decreases. For example, if I say with age, as kids are growing, the length of the femur is going to increase. So these two things go together. As you increase in age, as the child is increasing in age, the length of the femur is going to increase and the height is going to increase. Or I can say, as we age, our muscle mass is going to decrease. So one increases, the other one decreases. So either positive or negative correlation. When two variables are correlated, it doesn't mean that you have the same value. They're just correlating. But if the two variables are in agreement, then they are very close to each other. For example, this data set has two things, X and Y. X could be therapist 1 and Y could be therapist 2. So these are the measurements that they got for something. So these two numbers are definitely correlated and they are in agreement. If you look at this data set, the X and Y, this is 5, this is 10, 4, 9, 3, 8, 2, 7, and 1, 6. This is, there is some correlation between these two numbers, but there is no agreement between them as you can see. So, if we want a measure to be reliable, we definitely want both correlation and agreement, not just correlation. And this is how you graph this. This is perfect correlation and agreement. This is correlation but no agreement. There is a huge difference between Y and X. All right? Keep in mind that self-report instruments or self-report questionnaires are treated as instruments. So the depression scale, disability scale, balance scale, whatever scale is identified as an instrument. Even these instruments must be tested for reliability. So instrument doesn't mean just a goniometer or a isokinetic machine or a tensiometer or a dynamometer. It could mean a piece of paper that has questions. Instrument reliability is important, and there are several aspects of reliability for instruments. One is called internal consistency. From the name internal consistency means it should be consistent. So self-report instruments could be an instrument about quality of life. It is a questionnaire, paper and pencil type of instrument, and it's asking questions about quality of life. It could be physical activity limitation questionnaire, it could be perception of health questionnaire, could be any type of questionnaire. These instruments are designed to measure different concepts or constructs. So quality of life, there is no one question that's going to ask about quality of life. Quality of life has a few aspects. aspect that has to do with physical life, psychological life, cognitive life. So the instrument measures different concepts or different constructs. For example, this is an instrument called the Burden of Stroke Scale, or BOSS. It is designed to measure 3 different constructs or concepts or domains or subscales. One is physical, which is the physical activity limitation. The second is cognitive, that's the cognitive activity limitation. The third is psychological distress or psychological limitations. This is the scale right here, and as you can see in the scale, this is the final score, the burden of the stroke, and you can see that some questions are talking about mobility, self-care, and swallowing. So this part is a physical part, or the physical activity limitation part. This section is about energy and sleep, the mood, satisfaction, restriction, positive mood, negative mood. All of this is under psychological distress or psychological domain. And you will see that some questions are related to communication, cognition, and social relations. So this is all under cognitive activity or cognitive limitations. So as you can see, every domain has separate questions. You don't see one question from here related to here, or one question from here related to here. So this instrument has 3 different domains, and every domain is separate, and every domain has its own questions. So this instrument has consistent, I want to go back to this, has internal consistency. Okay? So the instrument reliability also sometimes is tested through 2 forms instead of 1. So the previous one, now this is 1 form, 1 instrument. Sometimes you want to test 2 instruments to compare them to each other, and that's why it's called the parallel forms. In parallel forms, of course, we're talking about self-report instruments. You get 2 instruments supposedly measuring the same thing, and you give the 2 instruments to the same individuals to respond to them, and then you compare the results to see if the 2 instruments actually measured or gave the same scores to the person. Sometimes people don't give the 2 instruments, they put them together, so they make a long form by adding the 2 types of or the 2 sets of questions, and they give them to the same person to answer them the same time, and that's this form is called the split half. As you can see from this, we're trying to compare 2 instruments to see if they are measuring, or the results are similar to each other, and if they are measuring the same thing. So that's another way of testing self-report instruments for reliability. So for a measure, if I'm measuring something or an investigator is measuring something, we need this measure to be reliable. Reliability, one more time, means the extent to which a measurement is consistent, stable, and free from error. High reliability is required for your measures, otherwise your error is huge. Reliability is important, but then you need that measure also to be valid. And validity is another thing, and a definition of validity, it is the extent to which a measurement measures what it is intended to measure. So validity means that the instrument that you're using is actually measuring what you are intending to measure. And we'll talk more about validity in the next section. Reliability is necessary but not sufficient condition for validity. You could be very reliable, but you're not measuring what you were supposed to measure. And that is validity. So you need both for your measure to be useful.